Hey, welcome back. In this video, we're going to look at functions. You've probably seen functions before in multiple previous math classes. For example, back when you study arithmetic, you look at some basic functions, which you can think of as taking inputs that are ordered pairs and giving an output, which is a single number. These functions, we call them addition, multiplication, subtraction, and so on. When you study algebra, like algebra 1 and algebra 2, you look at functions there too. Some of the most common functions you might see are f of x equals x and f of x equals x squared. You might try to see what is the intersection of two functions. For example, for these functions, if we wanted to find their intersection, we could set them equal to each other, x equals x squared, and we can solve that equation using algebra. In geometry, we also see functions. We see reflections and rotations, and we can think of those functions in geometry as taking shapes as inputs and giving shapes as outputs. In calculus, we also see a lot of functions because we need a function to take the derivative of and to integrate. And there's some derivatives, the first and second, and so on. In set theory, we see some functions. Cardinality is a function which takes a set and outputs an integer. The union is a function which takes an input, which is a pair of sets, and outputs a set. And same with the intersection. And in logic, we also see functions there too. We can think of truth values as functions. They take as inputs propositions, and the output is T or F. We can also think of and, or, like conjunction and disjunction, and negation. We can think of all of these as functions. And or, they take inputs which are ordered pairs of propositions, and their output is a proposition. And negations take inputs which are propositions, and their output is a proposition. So you have seen a lot of functions before, probably, but in this video, we're going to cover the definition of a function, just to make sure that we know what exactly a function is. And we'll also see some properties of functions and some special types of functions. So let's start with the definition. Suppose that x and y are non-empty sets. And we define a function from x to y. And this is just some map which assigns a single element of y to each element of x. If f is a function from x to y, we write f x right arrow y as so. And for each x in x, we write f of x equals y if y is the element of big Y that f assigns to x. And I want to underline a word here, the element. There's only a single element that this function maps each element of x to. And we're going to have these terms, which we'll use a bunch of times. When we have a function, which we write f x right arrow y, so a function which maps elements of x to elements of y, we call x the domain of the function, and we call y the codomain. And this a, I wanted to explain it. It's very important. If we have f of little x equals little y, where x is some element of big X and little y is some element of big Y, then we call little y the image of little x under this function f, and we say that x is a preimage of y under f. And notice that I used a there, and up here I use the, and here I use the as well. So the difference is that the preimage is not necessarily unique. There might be multiple x, multiple values little x in the set big X, which map to the same y. So this y might have multiple preimages. So this is why we have to use a instead of b. We can also define the image of the function f. So the image of f, and another name for image is range. It's defined as the set of values f of x for x in the domain, where the domain again is our set big X. And we can also define the image of a subset of our domain. So if S is a subset of the domain, we say the image of S under F is the set f of x for x in S. So now that we have all these terms, we're going to look at some example functions, and we will see what is the domain, what's the codomain, what's the image. So first, let f be the function defined by f of x equals x plus 1. And suppose we have f from the reals right arrow to the reals. So let's quickly go through like what's the domain, what's the codomain, and the other terms. So the domain, that's the set on the left. That's the real numbers. And the codomain is the same because both sets on the left and right are the same. They're both the real numbers. Now, the range is a little more interesting. The range is still the real numbers. Now, to see why that's true, we can see that every real number, little r, is the image of some other real number. And the real number that is mapped to r is r minus 1. We can also look at the image of a subset of the reals under this map f, and we can consider the subset being the integers. And if we have this function f of x equals x plus 1, the image of the integers under f is just the integers. And that's because every integer is the image of itself minus 1. And if we have some non-integer, it cannot be the image of any integer under the function f of x equals x plus 1. Because if x is an integer, then so is x plus 1. Can't get a non-integer. So let's consider another example. So for the second one, let's say we have this function f of x equals x squared. And again, we have f from the reals right arrow to the reals. So the domain of f is the reals. Same with the codomain. So this is the same for the domain and the codomain as the last function. The range, though, this is more interesting than the last one. The range is the non-negative real numbers instead of all the real numbers. We can see that because if you take any non-negative real number, you can take its square root. And its square root, if you plug it in as the input to f, you get the non-negative real number we started with as the image. So all of the non-negative real numbers are in the range. And we can see that any negative real number does not have a square root. So there's no value of x in the real numbers, which satisfies x squared equals a negative real number. I just want to underline this word here. So obviously, if we allow ourselves complex numbers, then we can have I as the square root of -1. But if we restrict to real square roots, then -1 has no real square root. And same with any other negative real number. And we can do the image of a subset. Again, we'll consider the integers. And the integers, let me draw them. So we have 0, -1, +1, -2, +2, -3, +3, and so on. The image of this subset of the reals under f, remember f is the square function. So that function sends 0 to 0. It sends ±1 to 1. It sends ±2 to 4. It sends ±3 to 9. And it sends ±4 to 16 and so on. So if we want the image of the integers under this map f, it's just this set. And these numbers are called the perfect squares. These are the integers which are squares of integers. So 0, 1, 4, 9, 16, 25, and so on. That's the perfect squares. So now we're going to consider some properties of functions. And like we did with the terms like domain and codomain, we will see some examples so we can study these properties. So the properties we're going to look at are injectivity, surjectivity, and bijectivity. First, let's start with what it means to be injective. So the function f from x to y is called injective if and only if every element of the domain has a distinct image. In math symbols, we can write this as f is injective if and only if f of x1 does not equal f of x2 for all x1, x2 in big X with x1 not equal to x2. And injective functions also have another name. They are called one-to-one. Now, before we go on to surjective functions, I want to draw a picture here. So sometimes the functions, it's nice to draw them with your left set and your right set drawn as circles or ovals. And we can illustrate injectivity with a picture of what we don't want. So let's say we have some distinct x1 and x2 in big X. So x1 and x2, they're not equal to each other. That's why I drew them as different points. And then let's say we have some y over here. And we can draw our f. One way to draw f is drawing it with arrows, showing which element of y is assigned to each element of x. And so the way we've drawn it here, we've mapped both x1 and x2 to the same element of y. And we're calling that element little y. And this is bad for injectivity. We don't want that. So that's the picture to keep in mind. You don't want that. And x through it. Now we're on to surjectivity. We say that f is surjective if and only if every element in the codomain has a preimage. So for this one, I think it's good to draw a picture for this too. Maybe I'll draw it earlier this time. So we got our x and y up here. And let's say I have all the elements in my codomain. We'll say it's pretty small. It only has 4 elements. Maybe I'll put a 5th one there too. Now, what does it mean to be surjective? We need every element of the codomain to have a preimage. So we need some x here to map to y1. We need some x to map to y2. We need some x to map to y3. We also need some x, maybe it's up here, to map to y4. And then we need any x anywhere that can map to y5. Let's say it's over here. So that would be surjective if that's all the elements of our set y. And it's okay if we have some elements that map to the same y. That's fine for surjectivity. So this is okay. These two are both going the same one. We can have one here, right here. It can go to this one up here too. So that's okay for being surjective. That's fine. We just need all the elements in the codomain to have some preimage. And we can say that in math notation, as for all little y and big Y, there exists a little x and big X with f of x equal to little y. And another name for surjective functions is onto. So if a function is surjective, it is also onto, and vice versa. Finally, the last term I wanted to mention is bijective. Bijective is easy to define because a function is bijective if and only if it is both injective and surjective. Now that we have these terms, we can look at some examples and we'll see whether they are injective, surjective, or bijective. Here's the first example. Let f be the function defined by f of x equals x plus 1, and f is from the reals to the reals. We can see that f is injective, and here's how we can test injectivity. We can start with an equation, f of x1 equals f of x2, and then we can take the definition of f, simplify that. Since f of x equals x plus 1, we can write f of x1 equals f of x2 as x1 plus 1 equals x2 plus 1, which implies that x1 equals x2. So if f of x1 equals f of x2, then x1 equals x2. The contrapositive tells us that if x1 and x2 are not equal to each other, then f of x1 does not equal f of x2. So that gives us injectivity. And this is how we can check injectivity for any function. And we'll see another example later. We can also see that f is surjective. The way to see that, for any element of the codomain, and the codomain here is the real numbers. So given some real little r, its preimage is r minus 1, and it has a unique preimage. And since f is both injective and surjective, we can say that f is bijective. F is a bijection. Let's look at another example. Here's a function f of x. It's defined as x squared, and f again goes from the reals to the reals. This one we can see it's not injective, and that's because we have many values which give us the same output. And when I say many values, I mean many pairs of values. So 1 minus 1, we plug them both in, we get 1 as our output. 2 and minus 2, we get 4 for both of them. 3 and minus 3 give us 9. So x and minus x always give us the same output for any real number x. So no injectivity, and also we don't have surjectivity for f going from the reals to the reals because there's an element in our codomain, for example, minus 1, that has no preimage. There's no value, a real number x, which satisfies x squared equals minus 1. Because like we said earlier, no negative real numbers have real square roots. And if we allow complex numbers, then negative real numbers would have square roots. But this function, notice that it's going from the reals to the reals, so we're not allowing complex here. So this function is neither injective nor surjective, so it's definitely not bijective. Now let's look at a third example. This third one will be the function f of x equal to e to the x. So the exponential function with base e, and f again goes from the reals to the reals. We can see that f is injective, and we can test the injectivity the same way that we tested it for the first function. We set f of x1 equals f of x2. We use the definition of f to write that as e to the x1 equals e to the x2. And then we can take the log of both sides. And log of e to the x1 equals x1. Log of e to the x2 equals x2. So we have x1 equals x2. So that means that if x1 is not equal to x2, then f of x1 does not equal f of x2 by contrapositive. On the other hand, even though f is injective, this f is not surjective. And that's because we can find an element of the codomain that has no preimage. For example, -1, because e to the x always gives us a positive number. So -1, we're never going to get -1 as an output for e to the x. Now on to the next topic. So we talked about bijections, and when you have a function which is a bijection, you can define another special function, and it is called the inverse function. So if f from x to y is a bijection, we have the fact that every element of the codomain has a preimage by surjectivity, and it must have a unique preimage by injectivity. So these two words followed by injectivity and surjectivity respectively. And that allows us to define this inverse. So I'll erase those words. So the inverse of f is the function, and we denote it f to the -1. And this function maps each element of the codomain, little y, to its unique preimage under f. So this function is well defined because every element of the codomain has a unique preimage. So there's only one choice, and there is always a choice. And we can see that f inverse of y equals x if and only if f of x equals y, because this y, it's mapped to its unique preimage. The preimage is the x which satisfies f of x equals y. So f inverse of y must equal x. And we can note that for all elements of the domain, all little x in the domain, we have f inverse of f of x equals x. That's because if we have f of x equals y, we also have f inverse of y equals x. So f inverse of f of x equals f inverse of y, which equals x. That's just from the last bullet. And similarly, for all little y in the codomain, we have f of f inverse of y equals y. So we're going to see some examples now. First example, consider this function f from the reals to the reals, which is defined by f of x equals x plus 1. We want to find its inverse, and we saw earlier that it's a bijection, so it actually has an inverse. To find the inverse, we can use this process, same process we can use every time. We're going to use this fact to find the inverse, this property that we want for it. F of f inverse of y has to equal y for all real numbers y. And f, the definition of f is f of x equals x plus 1. So when we have f of f inverse of y, we can simplify that. We're just plugging in the f inverse of y right here for the x up there. So we're going to get f inverse of y plus 1 on the left side, and that equals y. And that gives us the value of f inverse of y that we're looking for. We can write it as f inverse of y equals y minus 1, just subtracting 1 from each side in the previous bullet. And that's our inverse function. And we can notice that that one has that property we want. This one right here, it also has the other property we want, which is f inverse of f of x equals x. Because we see that f inverse of f of x, since the f inverse of y is y minus 1, f inverse of f of x equals f of x minus 1. and f of x is x plus 1. So we get x plus 1 minus 1, which is x. So this is the inverse of that f. Let's see another inverse. Here is f of x equals x cubed. And you can check to see that this is a bijection from the reals to the reals. So let's find the inverse, and we'll use the same process we just used. We're going to use the property we want, which is f of f inverse of y equals y. We're going to plug in with our definition of f. From that previous bullet, the definition of f tells us that we want f inverse of y cubed equal to y, because our function f is f of x equals x cubed, and we have an f right here. We just change that f of the inside to the inside cubed using the definition up here. And we can take the cube root of both sides. So we can raise both sides to the 1/3. And that tells us then that f inverse of y equals y to the 1/3. So that's our inverse function. And we can see that it has the other property that we want. In addition to this property, it has the property that f inverse of f of x equals x, because f inverse is y to the 1/3, f inverse of y. So f inverse of f of x is f of x to the 1/3. F of x is x cubed, so we get x cubed to the 1/3, which is x. So when you have functions, and the first function has codomain equal to the domain of the second function, or when the domain of the second function contains the codomain of the first function, we can define the composition. And the composition is defined pretty intuitively. So we define the composition of G and F here. We write it as G circle F, and we define it by G circle F for any input X in this set X, the domain of F. The composition of G and F is defined just to be G of F of X. So we put X as the input to F, we get an output from that, and we put that output as the input to G, and then we see what's the output of that. And that's our composition. And we're going to see some examples of compositions now. So first example, let's say that our function f goes from the reals to the reals, and it's defined by f of x equals x cubed. And we'll also consider a function g, also from the reals to the reals, defined by g of x equals x plus 1. We can compose these functions. We can do the composition g of f, and g of f is defined as so. So we just need to take for any real number x, g of f of x. And we see that g of x is x plus 1. So g of f of x is going to be f of x plus 1. So that's how we go from here to here. And then we take the definition of f of x equals x cubed. We plug that in here to get x cubed plus 1. So that's the composition of g and f. We can also do the composition of f and g. So f of g of x, we take the definition of f, and we write f of g of x as g of x cubed. Then we take the definition of g of x equals x plus 1. We plug that into the parentheses, we get x plus 1 cubed. So that's our composition, f composed with g. Let's see another example. Consider this function f from the reals to the non-negative reals, which is defined by f of x equals x squared. And consider the function g from the non-negative reals to the non-negative reals, which is defined by g of x equals square root of x. We can do the composition g of f, and this is written g of f of x, which equals, using the definition of g of x equals square root of x. We plug in f of x, so we get square root of f of x. And the square root of f of x, using the definition of f of x, is the square root of x squared. And the square root of x squared, we saw this previously. It's equal to the absolute value of x. So that's the composition of g and f. And this function, this composition, goes from the reals, the domain of f, to the non-negative reals, the codomain of g. Now what's interesting here is even though the codomain of g right here is different from the domain of f, we can still define the composition of f composed of g. And this is because the codomain of g is a subset of the domain of f. So even though that codomain of g is not the same as the domain of f, we can still do the composition f of g. And in order to calculate it, we just take f of g of x. So f of g of x, we use the definition of f. F is defined on all reals. And we know that g of x is a real number. G of x, in fact, is a non-negative real number, but any non-negative real number is real. So g of x is real. So f of g of x, since f of x is x squared, f of g of x is going to be g of x quantity squared. And then we can plug in our definition of g of x there. G of x is the square root of x. So we get the square root of x in the parentheses, squaring it, which gives us the x at the end. And notice the composition here. The composition f composed with g goes from the domain of g right here to the codomain of f, which is this right here. And notice that these compositions, they agree where they're defined. So the first composition, g composed with f, we got the absolute value of x. The absolute value of x equals x for x in the non-negative reals. However, these are different functions because these functions have different domains. So that's why these are different functions. These compositions are actually different functions because their domains are different. But where they are defined, where they're both defined, they agree. So they're the same where they're both defined, but one of them is defined in more places because this one is defined on all reals, and this one is only defined on the non-negative reals. So on to our final topic, and this one will be one that you will probably recognize because when you've looked at functions before, you've probably seen a lot of graphs. So if we have a function from x to y, our function f, we define the graph of f as the set of ordered pairs x comma y, for which x is an element of the domain, and f of x equals y. And we can draw the graph if we have a function from the reals to the reals, for example. And we can draw it just by placing a point in the plane at the coordinates for each element of that set, which we just defined, the ordered pairs x and y with x in the domain and f of x equal to y. So we're going to see some examples. First example, consider the function f from reals to reals defined by f of x equals x. The graph is just the set of ordered pairs x comma x, where x is a real number. And we can draw this. So usually when we draw functions from the reals to the reals, we draw them in the coordinate plane. Here's our x-axis, here's our y-axis. This will be, say, positive x minus x, positive y minus y. And now our function f of x I'll give it some scale here. So we'll say we got 1, 1, -1, -1. And here our function, I'm just going to draw it. I'm going to draw some points as guide points, and then I'm going to just go in a straight line for the rest of it. So that's roughly what our function f looks like. So to be more precise about it, we have a 45-degree angle there. We have a 45-degree angle here. This is a right angle. And I just want to note that these angles I drew are not part of the drawing of the graph. The only part of the drawing of the graph is this thing that I label f right here. So that's our graph of f, is that line I drew. And it is a line. In this case, our function f is linear, so its graph makes a line. Okay, let's see another example. Here's another function that we just saw. The function from the reals to the reals defined by f of x equals the absolute value of x. And the graph of this is just this set of ordered pairs x comma absolute value of x for x in the reals. We can actually draw that set as the union of a few sets. So we can say this equals the set of x comma x for x in the non-negative reals union with x comma minus x for x in the negative reals. We write the negative reals like this. And now I'm going to do a drawing. So this one I'll draw up here. There's our x-axis, our y-axis. We'll have our scale here. Okay, so we can draw that first set. That first set looks like the one we just drew on the previous slide. It's the ordered pairs XX, except it's only half of it. It's only for x in the non-negative reals. So we start from the origin, and then we can just draw going up this way, roughly. So we got a 45-degree angle there. The angle is not part of the drawing. It's just to clarify the drawing. And we also have to draw the points. So we drew these points already. Those are done. We also have to do these. The x minus x for negative x. So these we draw like this, roughly. And that's a 45-degree angle as well. So this is f. So is this. This is f over here. They're both f. Just f in different parts of the domain. And I will note here that this is also, that's 90 degrees. And so is this. It's 90 degrees. So that's a drawing of the graph of f. So that's all for this video. Thanks for watching.